Okay, sorry about all that. Okay, so let's look at the lithium ion or lithium elements. How many electrons does lithium have? Neutral lithium. Look in the periodic table up there. 6.3. No, that's the molar mass. 3 electrons. Okay, now let's recall Bohr's model of the atom. Bohr's model said the nucleus was at the beginning in the Google's listening. All right, and then remember Bohr, we had the planetary model, and the first orbit had maximum of 2 electrons, then the next one had a maximum of 8 electrons. Okay. So this is Bohr's model. Okay, now quantum mechanics said, well, we're going to subdivide those orbitals a little more. And the first one still stays the same, but the next one out, the second orbital, is subdivided even more. So really, it's subdivided into 2 main parts. One part holds 2 electrons, max. The next part holds 6 electrons. So it's still 8, but it's just subdivided. Okay. Now, when we start putting electrons in the orbitals, the most stable orbital gets filled first, which is the closest to the nucleus. Now, the reason why it's the most stable, or one of the many reasons, is because electrons are negatively charged. Nucleus has protons that are positively charged. So there's an attraction there. That's why the innermost orbital is most stable. And then once that is full, we have to go to the next one out, the next one out, etc. Okay, so we've got 3 electrons. Okay, we're going to put 2 electrons in the innermost orbital, and then we have 1 left over, so that's going to go here. Okay, so if we jump down to uranium, how many electrons does uranium have? Look at the very bottom, U. 92 electrons. So that's a lot of circles. A lot of circles. So we're not going to use that way of assigning electrons now. We're going to use a little different system. So, and again, this electronic configuration means that for every electron, there's going to be a unique identifier or configuration for that electron. So we've got 3 electrons for lithium. It means we're going to have 3 different configurations, 1 for each electron. Okay, now there's something called a shell. Okay, so the shell is the most general designation. When we divide shell up, we're going to come up with a subshell. When we divide the subshell up, we're going to come up with orbitals. Okay, the way the shells work is this is shell 1, this is shell 2. Now, I already mentioned that shell 2 is subdivided into 2 sets of orbitals. Okay, so we're at the subshell level now. And those are named S and P. Now, at shell number 1, there's only 1 orbital. So that's going to be S. Okay, so let's simplify this a little bit more. Okay, so an orbital can only have 2 electrons in it. So if this 2p has a maximum of 6, how many orbitals does it have? 3. 6 divided by 2 is 3, right? And then the last way to configure the electrons is what spin does it have? Now, interesting, electrons have a magnetic component. That's why some metals are magnetic and other ones are not. So if you have a magnet and then you try to put another magnet close to it, there are 2 ways to do it. A way which resists you and the other way attracts. When it attracts, the north pole is against the south pole of the other magnet. When it repels is when the north pole is against the other's north pole. So when we start putting electrons in these orbitals, we have to put them in there the most stable way, which is north to south. And that's the spin they're talking about. So the spin is going to be up or down, but opposite when they pair up. Now, what happens with a magnetic metal is that some electrons are left unpaired. And if they're left unpaired, that means there's some magnetism that's available, that's not been shared. And that's what makes metals magnetic. Okay, so there's 4 deals for each electron. And that came out of quantum mechanics. So that was the next model after Bohr, because Bohr's atom had some issues. Okay, so let's look at how we're going to do the electronic configuration for lithium. Okay, so we have 3 electrons to account for. Okay, 2 of them are in shell 1 s orbitals. And how many electrons are in there? 2. So this is the shell. That's the subshell. Okay, so we've accounted for 2 electrons. We have 1 more to account for. Where's the other electron? Next up.
So is it subshell?
It's in shell what? 2. Subshell what? S.
Oh, that's.
S is the most stable of the 3 orbitals in there. Okay, so we're going to go 2 S1. 2 for the shell. S for the subshell. And 1 electron. So, electronic configuration for lithium, accounting for those 3 electrons, is 1s2, 2s1. Now the top superscripts have to add up to 3. So you can see the complex math I'm talking about. 2 plus 1 is, so that makes sense. So this is electronic configuration. For lithium. Now, as we get more and more electrons, things get more complex. Yeah.
So for the two and the one above the like 1s and 2s, how do you know to put 2 on one and then 1 on the other?
Well, we have 3 electrons to account for, right?
Yeah.
Okay. 1s2 accounts for 2 of them. And then one more to account for. So we go to the next shell out to shell 2.
Oh.
And then within that shell, we go to subshell S, which is closer in. And then we put the 1 electron there.
First shell always has to.
Always. The next one out, let me back up. Maximum of 2. Say hydrogen has how many electrons? So it's not going to have 2 in it, it's going to have 1. Okay. How are we doing so far? All right, let's do another one. Let's do nitrogen. Okay. Now nitrogen's got what? How do we know how many electrons are in neutral nitrogen? What do we go by? Remember, there's 2 numbers, a decimal number and an integer. Which one do we use? The integer, yes, not the decimal one. The decimal one, as you remember, molar mass. Molar mass is always a decimal, except for man-made elements or person-made elements. All right, so let's look at nitrogen now. Nitrogen has 7 electrons. So we need to have a series of S's and P's now that add up to 7. So we start with the innermost orbital, which is an 1s2. That leaves 5 more electrons. 2s2. We got 3 more to go. 2p3. Okay. So we have 2 plus 2 plus 3 is 7. So we've accounted for all 7 electrons. Now, when we looked, remember we were doing,
I'm sorry, that's okay. So why did you put 2 first one?
because each orbital can only hold 2 electrons. So going back up here, see, this can only hold 2 max.
Okay.
And then we have 3 to account for. So we put the first 2 in the S, and then what's left over, we put in the P's. Sorry, what? Yes. Okay, her question is, why does P's can have more than 2? That's because P's have 3 orbitals, suborbitals. And 3 times 2 is 6. That's where they get the 6 from, because we have 3 suborbitals in there. Each one has a maximum of 2. We have 2, 2, 2 max. But we don't have enough electrons to go all the way out. We only have 7 electrons for nitrogen. So we can only put 3 in there. Now, yeah. Say again?
So
At this orbital level, you can only have 2 electrons. And Bohr says P has 6 electrons. Well, how can we figure 6? I just told you can only have 2. So we have 2, 2, 2. We have suborbitals within the P's. Each one can hold 2 apiece. That's where we get the 6 from. This is easy math, but it's very detailed. Okay. So let's explore this. Yeah.
Okay, so just so I'm understanding, the 1s2 is 1. Correct?
The first major orbital in is shell 1,
And then the second one, 2.
but 2 has extra stuff in it because it can hold 8 electrons.
I'm just trying to the 7 electrons. How do we get the 1s2? Like, is it supposed to, are those supposed to equal 7?
All of them together equal 7.
Because the 2p3 you said is 6.
It's like we have to divvy up the electrons. They have little pockets that can hold 2 electrons apiece. And we need an order to fill the pockets. We fill the pockets that are most stable first. So we go boom, boom, boom. We can fill 3 pockets full, and then we have 1 left over. We go 2, 2, 2, 1. Okay. In shell 1, that takes up one of the pockets. Shell 2 can hold 6 electrons. So there's 3 pockets in that P. Okay. S, the first one in is we're going to call S. The next ones we're going to call P's, plural. And there are 3 of them.
6.
Yeah. So I'm going to keep this thought now. Let's take now and revisit that P stuff. We are going to represent an orbital or what? Second one out. Okay, so let me explain this a little more and then you see if that answers your question. Okay, so we can represent the orbitals with either a box or a 0. I'm going to draw not as a circle or a box. I'm going to use circles. Okay, those are the little pockets we can store electrons in. Okay, so this says we have 2 electrons in here. Remember, we have to have them opposite when we go in there. Okay, that leaves 5 more electrons. Okay, the next, and this is so this is a shell. Okay, so we have 5 more to go. So we're going to go to the S first and totally fill it. And how many we have left over? 3. So there's 2 ways to fill those 3. We can put it like this, or like that. So which is more stable? Top or the bottom? Top is correct. Why do you think it's more stable?
Because everything equal.
Is everything is what?
Equal?
Yes, what else? That's right. Who was saying that? Oh, okay. Yeah. Nature likes symmetry in general, okay? Like in organic chemistry, you synthesize stuff but you usually get a mixture. And so you look at the structure of the mixture, and whatever's most symmetrical is more stable. Here we've got a nice equal distribution of that magnetic influx versus a lopsided one. So nature likes symmetry. So the top one is more symmetrical than the bottom one. Now back over 115 years ago, they came up with this stuff. Einstein was one of them. Fermi was another. A whole bunch of people. Bohr was one of them as well. Okay, so the way the P's are going to fill is first we put one in each one. If we have any left over, we go back in and then start pairing them up. There's a principle called the Aufbau principle that says that. But it's just, aside from all these names, just think strategically. What's most stable? Always think what's most stable. Okay, so this is what it's going to look like. Now, each P aligns to an axis. One P aligns along the X, another the Y, another the Z. So you'll sometimes see this referred to like this. Okay, so this is the orbital representation for nitrogen. Now, when we were doing Lewis dot structures, remember nitrogen looked like that? So there it is. There's the pair. 3 singletons. 1, 2, 3. So the Lewis dot structures align with the electronic configuration. When did we do Lewis structure? That was a while ago, wasn't it? Do we do that in unit 2 or unit 3? Lewis dot structures. 2? No, that was a while ago. Okay. All right, let's do another one. Are there any questions about nitrogen? Okay, so let's let's do sulfur. Now sulfur's got 16 electrons. 16. Okay, let me one last point to make with there are two kinds of electrons in all molecules, atoms. You have core and valence. And when we talked about fluid structures, we always talked about the valence electrons. Those are the outermost electrons. So you look at the shells. What's the highest number shell? In this case, it's 2. So that's the valence electrons. Everything else are core electrons. So now we're going to look at sulfur. Sulfur's got 16 electrons we have to do the configuration on. Okay, so that takes care of the first two. Now you're going to notice a distinct pattern emerging. Yes, keep that thought. All right, that takes care of 4. That takes care of 10. We still have 6 to go. So now we're going to go to the next shell out, which is 3. 2 there. And how many are left over? 4. So that would be the electronic configuration for sulfur. So this is valence, core. So let's look at the orbital diagram now for sulfur. So we've got so this is the S's, S, P, P, P. Now we have 4 electrons. We're going to spread those out. And then we have to pair up the last one. It doesn't matter which one of those you choose. Okay, so that's the orbital diagram for sulfur. Now, there's a distinct advantage in looking at the orbital representation, because you can predict from that what kind of ions sulfur likes. So tomorrow we're going to talk about in depth, why do ions form? We know that ions, the number of electrons and protons don't match. Sometimes you have more protons, sometimes more electrons, and that determines the charge. But why does that happen? Tomorrow, we're going to dig into that. Repeat, 6. Because you have 3 orbitals, 2, 2, 2. And what if we have 10? Two, 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 two. Yeah, exactly. The next level is going to be D. And guess how many it has? 10. The next after that is F. It has 14. Now in here, we're only going to go up to D. So we're not going to do any Fs. Your next class is going to do lots and lots of Fs. But I want to make sure your understanding of this is solid. Because Fs are tricky depending on what periodic table you're using. There are 2 periodic tables out there. And how they differ is in the Fs. Where do the Fs start? Where do they end? Okay, so that's sulfur. Valence electrons. Just as a harbinger of tomorrow, how much space do we have here? How many more electrons can we put in there?
2.
2. So that means if we were to form an ion, sulfur would like to have 2 more electrons. That means there's 2 more electrons and protons, hence the charge is -2. Guess what ion sulfur loves to have? -2. This is why. Now, tomorrow we're going to do a lot of examples of that. So I'm just saying, though, that so we have an opportunity with sulfur. So this is the neutral. not the ionic one. So tomorrow I'm going to talk about shell stabilities, subshell stabilities, etc. Okay, how are we doing with sulfur? Now notice the pattern here. These all look alike. Now let me show you something here. Yeah, are there any questions before I go on? Okay, I'm going to show you something ugly. Uranium. 92 electrons to account for. Let me show you what the electronic configuration looks like for those 92 electrons. Okay, so that's the electronic configuration for uranium. Only a mother could love that. Okay, so let's look at valence electrons. What's the highest shell we're talking about here? Shell number.
Oh,
What's the highest shell? Look at the very end. 7. Highest shell is the valence electron. So that's the valence core. So chemists don't care about the core electrons because they're extremely stable. So they stay in place. The valence electrons are not stable. And they want to do something to become more stable. That's why we have chemical reaction. Those valence electrons want to become more stable. Okay.
Is that a 5D?
5D, as in dog, yeah.
Does it know?
Oh, excuse me, I made a mistake. Should be F. Because it's down on the F's on the bottom. Okay, so I don't know if you noticed, when we get to here, you 4s2, and then look what happens. Look, we go from 4 to 3. That's what D's do. They go down 1. And F's go down 2. So I always say, to remember the letter, think of dumb. What letter does dumb begin with? D. So that group is dumb down 1. And then what's lower than dumb? Flunky, Fs. So there you go down 2 when we're doing the configuration. All right, we're not doing Fs in here. I just wanted to show you uranium though, because we have to account for all 92 of those electrons. So if we were to add up all the super scripts, they're going to add up to 92. You have to count for all 92 electrons. All right. Now there's 2 ways to write this electronic configuration. So we're going to go over to here and you might want to take a periodic table if you have one. I'm going to show you a technique one of my students developed 20-ish years ago. I still use it today. Her name was Chris. She had 3 kids. She was single and she worked full time. And she got all A's. I don't know when she slept. But anyway, this is the technique. She used to help a lot of students in groups. And this is the technique she came up with. First of all, we're gonna label blocks of electrons. So these guys here that, including helium, is called the S block. P block. Excuse me, P block. P block is over here. And then lastly, we have F block. Now, the reason why we blocked off those electrons is because we're going to take a journey, and the journey is going to be along the periodic table. And this was a technique, this student of mine, because she has young kids, she'd always talk to them with little parables. And this is what she came up with. Okay, so we're going to go on a journey. Let's look at sulfur now again. And we're going to take a ride along the periodic table to sulfur. So where do all journeys begin? They begin at the start. So what's the start of the periodic table journey? H. Element number 1, H. And as we go along that journey, you're going to be writing down the blocks you run into. So we start at H. That's shell 1. And how many elements do we go through? 2. We're not done yet. We're not at sulfur yet. So now we're going to go to shell number 2. We went through S block, P block. Now we're going to go to shell 3. So we're 4 into the P block. Now this works every single time, no exceptions. So as you go along, you just record. Now, most textbooks don't teach it this way. They have this little diagonal thing that you have to memorize. As you know, I don't like memorizing. You don't have to memorize. You just take a periodic table and you're going and just write down, as you go through the blocks, you just write them down. And when you get to the element you're interested in, stop and count how far into that block you've gone. Yeah. Hmm?
Oh. Okay.
It is 3P4. Wouldn't it be 2? So we have the P block, right? 1, 2, 3, 4, or 4 into the P block. Three is a shell. That means we're the third row down. And then which block are we in when we end? Well, we had to go through the S block to get to the P's. Well, sulfur's in the middle of the P. So how far in do we go? 4 in. That makes sense?
Yeah.
So basically the shell is what row we're on. The superscript, well, what row we're on is the shell. And then what subshell we're on is like S, P, D, F. And then how far into that block are we? That's the superscript. Yeah.
So that's the second. The P6.
Well, you could either do it like that or like this. Is that your question? Oh,
Does it look like the P5 stuff?
well, it was part of the, yeah. Okay, so notice that these keep repeating. So I'm going to show you something that's kind of interesting. If we look at neon, so this is sulfur. If we look at neon, we're going to go 1s2, 2s2, 2p6. That's for neon. It's exactly the same as this for sulfur. So a shorthand way of writing this is to go oops. That. Yeah. Yeah. So you want to use the electronic configuration of the nearest noble gas. To find it, you go up a row and to the end. So the nearest noble gas configuration is, see, all these repeat. The pattern repeats. So we're going to take advantage of that repetition by substituting in the noble gas configuration, which doesn't change. It's always the same. So they're the same. Oops. So one is just an abbreviation because we don't care what the core electrons are because they aren't doing anything. The valence electrons rule the roost. Valence electrons do all the chemistry. Core electrons do none other than contribute mass. They live a very boring life. Valence electrons are on the edge because they're always seeking to become more stable. To become more stable, you bond with something, or you transfer electrons, or you share electrons, but you don't remain unbonded because that's unstable. Okay, so let's do one more. Only this time we're going to use the enhanced one or the abbreviated one. So this is the abbreviated. Okay, so let's look at silicone right here. Okay, silicone's got 14 electrons. So what's the nearest noble gas? You go up a row to the end, those neon. So here's silicone, we go up a row and over to the right, neon. So let's do it the long way first. There's silicone's two in. Okay, so that's the long version. The abbreviated version is going to have core, valence. The core is going to be represented by neon. So valence, core. Makes sense? Now I've got a whole bunch of practice for you, like always. Okay, so we've got electronic configuration here. That's one, kind of explains it. Some questions and some practice. And then also, there is this one here. And those are the answers. And the only problem with this one, it's got F's in it too. So what I need to do is give you one that doesn't have F's in it. So I'll upload a replacement for that. Okay. So what I'd like you to do tonight for your Friday night gig is to practice this a little bit, because tomorrow we're going to get into more depth on this. We're going to get into ionic electronic configurations. And those require more understanding of what is stable subshell wise and what's not stable. And now at the end of lecture tomorrow, you should feel comfortable in saying, this is why this forms a -1 ion. This is why it forms a +4 ion. But you got to know what we learned today first with the neutral configurations. Okay? Yeah.
Can you update? Or do you want us just to do one that's in here?
Let me try to do that in combination of lab and tonight. So by the time you get home, you should hopefully have something. All right.